Welcome back, and in this video we are going to learn some of the results on equivalence relation. So we already have seen equivalence relation and equivalence classes. So we'll quickly go over through the some of the results on equivalence relation. So let's say we have a set and A, and it has a cardinality of n. So total number of elements present in set A is n. So there is a one to one correspondence between number of equivalence classes on A, number of equivalence classes on A, and number of partitions on A. So if we have n number of partitions on A, so there will be n number of equivalence classes on A. So for each partition, there will be an equivalence class, right? And that can be obtained by multiplying the partitions with each other. Like if we have a partition on A defined as 1, 2, okay, and 1 2 and 3 4, this is a partition. So equivalence class corresponding to this partition could be uh, 1 2 cross product with 1 2 union 3 4 cross product with 3 4, right? So this set containing the union of these two will be the equivalence class. So there is one to one correspondence between number of equivalence classes on A and number of partitions on A, like that. Okay. The second result is we can explain this as since a given partition of a given partition on A, we can find ER on A, like what I have just illustrated. We can find equivalence relation on A, and given an ER on A, we can find the corresponding partition. Okay. So on A, so there is a one to one relation between number of equivalence relation on A and number of partition on A. For each partition, there will be an equivalence relation. There is an equivalence relation, and for each equivalence relation, there is a unique partition, right? Now let's say if the cardinality of A is n, so number of ER on A is equal to number of partitions on A, and that is equal to Bell number. Okay, now what is this Bell number? So Bell number can be calculated as Bn equal to from k equal to 0 to n minus 1. Okay, n minus 1 C k and then bk. Okay, so b0 is equal to 1 and b1 is equal to 1. So n minus 1 ck and then cross product with bk. So this is the Bell number. So this way we can determine the number of partitions on A. Now how to calculate it? Like for every we need to calculate b1, b2, b3, right? Before, so on, like that. Okay, so this way we can calculate the Bell number. So n denotes the cardinality of A. So sorry, n. Okay, so if n has 3 component, we can calculate the b3. If n has 4, we can calculate b4, like that. So let's say if considering the same formula, let's say that if we have A consisting of 1 2 3, then it's we need to calculate the b3. Okay, and b3 we can calculate like b3 equal to k equal to 0 to 3 minus 1, that is 2, and then 2c 0 multiplied by bk. Bk is what? Bk is a 0. Okay, so we need to calculate, I mean we have to sum up like this, not like this, like uh, uh, b3 is equal to 2c0 cross product with b0 plus 1c1 cross product with b1, thus uh, 2C2, okay, cross product with B2. So K is here. So in this way we obtain 2C0 is 1, right, plus 2 into, sorry, it's 2C1. So 2 into 1 plus 1 into 2, and that equal to 5. So we calculate B3 as 5. So this way the total number of equivalence relation on A is 5. So this is the way we are denoting the equivalence relation. That's about this. And the next is, if we have the cardinality of A is defined as n, so smallest equivalence relation on R, on A is delta, that is uh, 1 1 2 2 3 3 dot dot up to nn, and elements number of elements in smallest er will be equal to n, okay, because for each element we are making it delta, we are performing delta operation, okay. And if we consider the largest equivalence relation, so it will be definitely A cross A, right. And if we calculate the number of elements in largest equivalence relation, then that will be equal to n square, okay. So this is an important result, largest and smallest. And the fifth point is that if R1 and R2 are two equivalence relation, okay, so definitely R1 and R2 will be reflexive, symmetric, and transitive, and therefore an equivalence relation. So what will be R1 intersection R2 and what will be R1 union R2, okay. So for this, if we calculate R1 intersection R2, so it will be reflexive, it will be symmetric, okay, it will be transitive, and it will be an equivalence relation. But for R1 union R2, it will be reflexive, it will be symmetric as well, but for transitivity need not to be, okay, need not to be, and for equivalence relation it also need not to be. So these are some important results. The most important what I found in these kind of result is about the Bell number that we need to remember. And the second thing is, there is one more result that I would like to discuss, and that is that if let R be an equivalence relation, let R be an equivalence relation on A, and AB belonging to A, then first thing is A belongs to A, okay. Second is A belongs to equivalence class B, then B belongs to equivalence class A, right. I mean the if A belongs to equivalence class of B and B is the equivalence class of A, and third is A belongs to equivalence class of B, then A is equal to B, and fourth is if equivalence class of A and equivalence class of B are equal, or if it is phi, I mean this is phi, okay. So these are some of the results that we can obtain. Important thing to note is the Bell number that is used to calculate the number of equivalence relation on R, or a number of partitions on R, and it is given as Bn, and you have to do k equal to 0 to n minus 1, n minus 1 ck into bk, okay. This is an important thing. And b0 is equal to 1 and b1 is equal to 1. So this is how you calculate number of equivalence relations. So this is all about some results on equivalence relation. And if you do have any comments or question, please keep posting. Thank you very much.